Take a pot of water and set it on the stove. Turn the heat to high and wait. At exactly 100 degrees Celsius, something extraordinary happens. Those liquid molecules suddenly have enough energy to break free and become steam. Not 99 degrees, not 101, exactly 100. And here's what nobody really sits with. That number isn't arbitrary. It's determined by the electromagnetic force, the mass of electrons, the way quantum mechanics allows atoms to bond. Change any of those fundamental values by even a fraction of a percent, and water wouldn't boil at 100 degrees. Actually, water wouldn't exist at all. Neither would you, neither would anything. The universe runs on numbers, about 30 of them to be precise. Fundamental constants that determine how reality operates at every scale. The strength of gravity, the mass of an electron, the speed of light, the electromagnetic force that holds atoms together. And here's the thing that keeps physicists awake at night. These numbers appear to be astonishingly, inexplicably fine-tuned for the existence of complexity, chemistry, and life. We're not talking about convenient coincidences. We're talking about precision so extreme that if you change some of these values by 1 part in 10 billion billion, the universe would be fundamentally incapable of producing anything more interesting than hydrogen gas. And we have absolutely no idea why. Let's think about this carefully because the implications are genuinely strange. Start with gravity, the weakest of the fundamental forces, but the one that shapes cosmic structure. Gravity is about 10 to the 36th power weaker than the electromagnetic force. That's a 1 followed by 36 zeros, which seems random, maybe even wasteful. Except here's what happens if you strengthen gravity by just 1 part in 10 to the 40th. Stars burn 1,000,000 times faster. The sun would exhaust its fuel not in 10 billion years, but in 10,000. Complex chemistry wouldn't have time to develop. Planetary systems would be unstable, life would be impossible. Weaken gravity by the same tiny fraction, and stars never form at all. The universe expands so quickly after the Big Bang that matter never clumps together. No galaxies, no solar systems, no planets. Just an infinite, dark expanse of isolated hydrogen atoms drifting through space forever. That's one constant. We have 29 more, and the pattern holds for nearly all of them. Consider the strong nuclear force, the glue that binds protons and neutrons together in atomic nuclei. It's calibrated to a precision that makes the gravity example look loose. If the strong force were 2% stronger, protons would bind together so readily that hydrogen would be rare in the universe. No hydrogen means no water, no organic chemistry, no stars burning through fusion. Everything would rush toward iron and stop there. If the strong force were 2% weaker, atomic nuclei couldn't hold together. Only hydrogen would be stable. No carbon, no oxygen, no nitrogen, no chemistry at all. 2%. That's the margin between a universe filled with possibility and a universe that's essentially a cosmic dead end. The electromagnetic force, the one responsible for chemistry, for the way electrons orbit nuclei, for molecular bonds, shows the same uncanny precision. Alter its strength by 4%, and carbon becomes unstable. Carbon, the foundation of all known life, the element that forms more compounds than all others combined, simply wouldn't exist in stable form. The organic chemistry that makes biology possible would be literally impossible. And this is where it gets particularly interesting. These constants aren't connected to each other through any theory we currently understand. The strength of gravity has no obvious relationship to the mass of an electron. The electromagnetic force doesn't clearly derive from the strong nuclear force. They're independent values, as far as we can tell, which means each one had to land in its extraordinarily narrow, life-permitting range separately. The odds of this happening by chance, if these values were randomly assigned, are so small they make winning the lottery look like a certainty. Physicists have calculated some of these probabilities. The cosmological constant, the value that determines the rate of cosmic expansion and is deeply connected to dark energy. Appears fine-tuned to about 1 part in 10 to the 120th power. That's a precision equivalent to throwing a dart at the universe and hitting a target 1/trillionth of a trillionth of a trillionth the size of a single proton. And somehow, reality threaded that needle. Well, it turns out we can observe the consequences directly. The ratio between the electromagnetic force and gravity determines whether stars can form planets. Too high and electromagnetic repulsion prevents matter from clumping. Too low, and gravity crushes everything into black holes. The actual ratio sits in a sweet spot so narrow that shifting it by 1 part in 10 to the 40th eliminates the possibility of stable planetary orbits around long-lived stars. The neutron is 0.14% heavier than the proton. This tiny mass difference is what makes chemistry possible. It's why neutrons decay into protons in free space, but remain stable inside nuclei, creating the diversity of elements. If neutrons were 0.2% heavier, they'd decay before nuclei could form. If they were 0.1% lighter, protons would decay into neutrons and hydrogen would be unstable. The entire periodic table depends on getting this ratio right to within a fraction of a percent. If questions like these are what keep you up at night, consider subscribing. We explore the biggest scales and smallest mysteries every week, always starting from what seems simple and following it as deep as it goes. So what's actually happening here? Scientists have proposed 3 main categories of explanation, and the remarkable thing is that none of them are fully satisfying. The first is pure chance. Maybe the constants really are random, and we just happen to get incredibly lucky. The problem with this explanation is scale. We're not talking about unlikely. We're talking about odds so extreme that unlikely becomes meaningless. 1 part in 10 to the 120th is a number so large that if every atom in the observable universe represented a separate lottery ticket, your chances of winning would still be effectively 0. Saying this happened by chance requires accepting a coincidence so extreme it feels like giving up on explanation entirely. The second explanation is the multiverse. Perhaps our universe is just one bubble in an infinite foam of universes, each with different values for the fundamental constants. Most of them are dead, sterile voids where nothing interesting can happen. We find ourselves in this one not because it's special, but because this is the only type of universe where beings capable of asking the question could exist. It's selection bias on a cosmic scale. You can only wonder about fine-tuning in a universe fine-tuned enough to produce wondering. This explanation is elegant in some ways. It removes the need for cosmic coincidence by creating infinite trials. Somewhere in the multiverse, some universe had to win the lottery, and we're in it. The trouble is that the multiverse is currently unverifiable. We have no way to observe other universes, no method to confirm they exist. It's a scientifically motivated idea that may be permanently beyond the reach of scientific testing. And this makes some physicists uncomfortable. It feels like replacing one mystery with an even larger unprovable assumption. The third category is more controversial: design. Maybe the constants are fine-tuned because something fine-tuned them. This isn't necessarily a religious position. It could be that we're in a simulation, that advanced intelligences created this universe deliberately, that there's some deeper mathematical structure we don't understand that necessitates these values. But it faces the same challenge as the multiverse. It's difficult to test, and it doesn't really solve the problem. It just pushes it back a level. Who designed the designers? What fine-tuned the simulation parameters? And here's what this actually means for us. The scientific community genuinely doesn't know. There are brilliant physicists who find the multiverse compelling. There are equally brilliant physicists who think it's untestable philosophy dressed up as physics. There are researchers exploring whether these constants might be connected through some deeper unified theory we haven't discovered yet, some mathematical structure that would make their values inevitable rather than arbitrary. And there are scientists who simply sit with the question, acknowledging that it's one of the most profound mysteries in all of science. Current estimates suggest we've identified around 30 fundamental constants, the free parameters in the equations that describe reality. At least 15 of them show apparent fine-tuning at levels that strain credulity if you assume they're random. The more precisely we measure these values, the more remarkable their balance appears. The Large Hadron Collider continues to confirm that particle masses and force strengths fall exactly where they need to be for stable matter and complex chemistry. Let's sit with that for a moment. Everything you've ever experienced, every thought, every sunset, every conversation, every moment of joy or suffering, depends on about 15 numbers being precisely calibrated to within microscopic tolerances. Change any of them by a tiny fraction, and reality as we understand it becomes impossible. This isn't speculation. This is mathematical fact derived from the equations that govern particle physics and cosmology. We can calculate exactly what happens when you adjust these constants, and the results are unambiguous. Nearly all possible values lead to universes far simpler and emptier than ours. Which brings us back to the central question: why these numbers? Why this universe? Astrophysicists have calculated that if the entropy of the early universe had been slightly higher, structure formation would have been impossible. If it had been slightly lower, everything would have collapsed into black holes within the first few million years. The actual value sits in between, allowing for 14 billion years of cosmic evolution that produced galaxies, stars, planets, and eventually consciousness capable of questioning its own existence. We don't know if this is accident, necessity, or design. We don't know if there are other universes where the constants differ. We don't know if there's a deeper theory that will someday explain why these values couldn't be anything else. What we do know is that the universe appears optimized for complexity in a way that our best theories don't predict or explain. Drop a comment and tell me what you find more compelling: the multiverse, pure chance, or something else entirely. Because this isn't a settled question. It's an open mystery at the heart of physics. And maybe that's okay. Maybe it's appropriate that the deepest question about existence, why is there something rather than nothing, and why is that something capable of producing us, doesn't have an easy answer. The universe took 13.8 billion years to produce beings capable of measuring the electromagnetic force to 15 decimal places and noticing that if it were infinitesimally different, those beings wouldn't exist. We're here now, able to see the knife edge we're balanced on, able to measure the constants, calculate the odds, sit with the profound strangeness of a universe that seems, against all probability, to have gotten every crucial detail exactly right. That might be coincidence, it might be necessity, it might be something we don't have words for yet, but it's real. The numbers are real. The precision is real. The mystery is real. And unlike cosmic horizons or black holes or quantum mechanics, this one doesn't require a telescope or particle accelerator to contemplate. It's encoded in the boiling point of water on your stove, in the stability of the carbon in your body, in the fact that gravity is exactly weak enough to allow stars to burn slowly and planets to orbit stably. Scientists can't solve it, not yet, maybe not ever. And sometimes the most honest response to the deepest questions is simply to acknowledge the mystery, maintain the wonder, and keep looking for answers.